Hello everybody, I am going to discuss this video. Actually this video is based on a problem on electrostatic force or Coulomb's force. I have discussed several videos. I have discussed several problems in my previous videos. Those are also based on electrostatic force. But this is a new type of problem based on electrostatic force, Coulomb's force. We have three steps to solve this problem. First thing is that to understand the question exactly what's actually the question is telling us. Second, how to go through the solution. And third, do the calculation in numerical way to get the answer. Now our first job starts what actually the question is telling us. What are the ingredients given in this question and what I'll have to find. This is a setup. This is our setup. This is an insulating stand. This is an insulating rod having length L. There are two charges. One is positive small q and this positive 2 into small q are mounted at the end of this rod having length L. And it is placed just at a distance L by 2 over the insulating stand. There are two equal charges beneath this charge and beneath this charge. These two charges are parallel to the insulating stand. These two are positive and they are also Q, but this is capital Q, and you can see that the magnitude of this charge and this charge are different. This distance is L by 2, this distance is L by 2, this is L by 2, this is L by 2, this total is L. Now, I'm going to hang a mass here, M, at a distance x from this positive small q. Then my question is telling me to find the value of x so that the setup will be in equilibrium. Means equilibrium means neither any force is acting in this system, neither any torque is acting in this system. This is the question is telling me. My job is to find the x in the equilibrium setup. Now come to the second point. Second step, that is qualitative analysis. How I'll have to go through this question, how I solve this question. See this, as we know the question falls in the section Coulomb's law or electrostatic force, we'll have to use that concept. But here a new concept, that equilibrium of forces concept. Those who you are aware of mechanics, they are easily handling the situation that we have to use equilibrium of forces concept here to set up this charge system into equilibrium. First of all, we have to know the conditions of equilibrium of forces in mechanics. Then we have to proceed. Now my quantitative analysis, third step to solve such problem. Whenever your question is quite lengthier, you have to do all the three processes. First process, to understand the question exactly, to find out what's given inside the question and what we have to do. What do we have to find out? Second thing is qualitative analysis. We have to understand the question, proceed through it, and identify the concept which are useful to solve the question. Third step is to do numerical calculation, to give the qualitative analysis in a numerical format to get the answer or what the question is demanding. I'm going to do quantitative analysis here. First of all, we have to identify the forces here. What are the working forces in this setup? See, these are two charges. Both are positive and they are separated at a distance L. So this charge repels this and this charge repels this. The force over this charge by this charge to repel it, that is F1. Force over plus Q by this charge is F2, and as we know, Coulomb's repulsion or attraction are mutual forces. So F1 and F2 are equal in magnitude and opposite in nature. There are another forces also. This is a positive charge, this is also a positive charge, so they repel each other. And the force applied by this charge over this charge is F3 in this direction because it's repulsion. Here plus Q, here plus 2Q. These are also forces. This force repels this charge. This charge repels this force. and that force is indicated here in F4 direction. Now, a last force. The mass is hanging here, so gravitational pull of this mass mg is downward. So this is mg downward. So we have 5 active forces here. So to put this setup into equilibrium, we'll have to bring all these forces to 0, means setup is in equilibrium by the forces. And after that, we'll have to search torque. All the torque by these forces in this setup should also equal to 0. Then we get the exact equilibrium condition. Let's see now. Our x-axis is here, our y-axis is here, our negative x-axis is here, our negative y-axis is here. Our positive z-axis is here and negative z-axis is here. Out of this plane and into this plane. Let's see. For equilibrium, we know from mechanics that we have to achieve this condition. As we all are familiar with mechanics, we know to achieve the setup in equilibrium of forces, we have to achieve the 6th condition. All the forces along x, y, and z axis should be 0. All the torques along x, y, and z axis should also be 0. If we have the 6th condition, then we can transform the 6th condition in more easier and handier way. That is this. So we have to work by this. If we have all the 6 conditions given, then we can use this 3 condition instead of the 6 condition. That's the concept of mechanics here. Now my board is sore. I need space for further quantitative analysis. So I'm erasing some part. Let's see. We are on the verge of solving the question. We have to write total force along x-axis should be 0. So total force along x-axis is F1 is in positive x-axis, F2 is in negative x-axis. See here. F1 minus F2 is equals to 0. Therefore, F1 is equals to F2. Now, total force along y-axis should be 0 here. There are 2 forces, F3 and F4, on this setup going in positive y-axis, and 1 force mg in this setup going negative y-axis. So F3 plus F4 minus mg is equals to 0. Therefore, F3 plus F4 is equals to 0. This is our condition. Fine.
Is equals to mg.
Oh, sorry. It's my mistake here. Is equals to mg. And these things have been cleared. My sister, she is supporting in this video. This is our joint venture. We both do our work to maintain the videos or to make this video. See, Tz is equals to 0. We'll have to achieve this condition also. Here's the concept. You can ask me the forces are along axis, so we can balance it according to given condition. The total forces along x and total force along y axis should be 0. But torque and angular momentum are always related to a point, to a spatial point. So in this setup, I need to show torque along z axis should be 0. Respective to which point? That is the question. Respective to which point? Then, according to mechanics, whatever I learned, if the setup is in equilibrium, then we can show the torque along z-axis is equals to 0 at each and every point in the setup. Anywhere, suppose here, 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 anywhere in this setup, you can show Tz is equals to 0. But the best way to pick the point is that suppose I'm taking torque at this point to be 0 along z-axis. How many forces are here? 2 forces. So these 2 forces will become meaningless for torque. Then I have to use these 3 forces. If I take my point here, there is only 1 force, so this force becomes meaningless, and I'll have to deal 4 forces to find the torque. If I'm taking my point here, there is no force. So this 2, this 3, this 2. All the 5 forces have torque at this point and they equals to 0. So it's easier to show torque along z-axis is equals to 0 related to the point which is max number of forces. That is our job. So I'm going to do it here so that my 3 and 4, these 2 forces will be meaningless to provide torque here. These 2 and these are responsible here. Tz is equals to 0 and this q at plus q. And as we know, the torque is a vector, so we can determine its direction by right-hand thumb rule, cross product direction. Here, these 2 forces have no torque. First force is mc. Check it. This is moment term for mc, and this is the direction of force. So this torque is in negative z-axis, minus x mc. Torque by mc at point plus q plus small q is this. It's along negative z-axis, so I have written minus. The torque is negative. Those who you are aware of torque and angular momentum, they understand what is the importance of momentum to find the torque. Momentum is the perpendicular distance to the line of force passing through the point where I'll have to calculate torque or angular momentum. See, there are 2 forces, F1 and F4, to produce torque at plus Q. F1 is in the line of the point, so F1 has 0 torque here. Now see F4. F4 is here, and the momentum for F4 at this point is capital L. And by using right-hand thumb rule, this forefinger shows the direction of momentum, this middle finger shows the direction of force, and this thumb shows us the direction of torque. See here, F4 is upward, L is here from this point, and this is the direction of torque. Means torque is positive here, along positive z-axis. L into F4 is equals to 0. Therefore, our x is equals to L F4 by mc. This is the value of x. I have solved the question, but you can ask me, you have a dot in your mind that x is still in a variable, that is F4. So I'll have to reduce this variable F4 from here, from this equation, with the help of this equation. But our job has been done here. We have this is equation 1, this is equation 2, and finally this is our answer, so we can tell this is equation 3. Momentum, torque. We need a lot of mechanical concept here to solve this problem. The problem is in the section of electrostatic force, but we need a lot of mechanical concepts. X is equals to this. Now I need to erase some space here, leaving something. I need this space. So x is equals to LF4 by MC. This is my x, but x contains a variable F4. I'll have to resolve that variable from equation 2. From what? What happened? Is it not recording?
Yeah, it's recording.
So I'm on the verge of the end. F3 and F4 are Coulomb's repulsion, so I can replace these values by Coulomb's repulsion. As we know, the distance between this plus Q and this plus capital Q is h here and h here. So I use this value to find the force here, Coulomb's repulsion. C in F3, 1 by 4 pi epsilon naught capital Q small q by h squared The force F3 is here. Similarly, the force F4 here. This is first charge, the second charge, this is distance. Q by h squared is equals to mc. Therefore, 1 by 4 pi epsilon naught 3 q by h squared is equals to mc. See, this value is equals to mc. This value is equals to mg. From here, q by 4 pi epsilon naught h squared is equals to mc by 3. So we get this value is equals to mc by 3. Now come here. I'll have to put this value just here to solve the x completely numerical values. Let me try and remove this because I have applied 1 and 2 here, so I need to remove this. X is equals to L F4 by mc. What's the value of F4? Put that value. F4 is equals to 2q by 4 pi epsilon naught h squared by mc. And see here, from here I can replace this value by mc by 3. So I can replace this value by mc by 3. mc by 3 2mc by 3 means this whole value is replaced by mc by 3 from here because I have driven this here from equation 2. See, mc cancel, so therefore x is equals to space. Therefore, x is equals to 2L by 3. So, x is equals to 2L by 3. Our question has been solved. What do we get here? Finally, x is equals to 2L by 3. So, x is equals to 2L by 3. This is our solution. And I'm sorry, you can see it's not over the insulating stand, it's to that side of insulating stand. So 2L by 3. This is for next mass. If you are having some different mass, you have to put the value and calculate the same way to get the value of x. So I have completed this question. Suggest my errors, and if you find any mistake in it, then suggest me. I welcome your comments and I welcome your suggestions to improve my knowledge. Thank you. Thanks for watching.